All of calculus involves limits, whether it's directly, like we're going to be doing here in the first unit, limits, or indirectly when we're doing derivatives and there are limits going on behind the scenes. So Unit 1, Lesson 0 is what is a limit. So by the end of this, you should be able to evaluate limits numerically. I think that's the best way to talk about what a limit is, rather than kind of the magic skipping over part. You should be able to use correct limit notation, or at least start trying to use correct limit notation, and you'll be able to use the formal definition of when a limit exists. That's definitely something that's going to be asked about. So watch out. While a lot of times when we're saying, hey, what's the limit? We want one output as the limit. A limit is a process. So you want to be thinking, you should be thinking about, hey, these inputs, the sequence of inputs, gives me the sequence of outputs, and I know where those outputs are going. So don't shortcut that, or it's going to come up to bite you later. Even if you can tell, hey, if I just substitute in one number, I can pretty much see what's going on, you're not really doing a limit. So I guess the first thing is, how do we read this? And you'll notice this is a one-sided limit. And we read this as the limit as x approaches 3 from the left. As in, if you had a number line, that's not what I want. If you had a number line, and 3 was right here, we're going to choose numbers approaching 3 from the left, or approaching 3 and just a little bit less than 3. You could say the limit as x approaches 3 from the negative side. I think it's better to say from the lesser side, or the left-hand side. Negative, we're not really using numbers that are negative. I just don't like the word. Anyways, so limit as x approaches 3 from the left of x plus 2. The other thing you'll notice is there are parentheses around x plus 2. That way this limit applies to the x and applies to the 2. We want to make sure we're always writing that stuff. Okay. So in order to do this one-sided limit, and it's one-sided, we'll do the other one-sided limit in a moment. The limit as x approaches 3 from the right. We're only approaching 3 from one side. So we think of some number that's close to 3, but not exactly 3. We'll get to that in a bit once we have the idea of continuity. And, well, what number is a little bit less than 3? 2.9. And so, well, what's 2.9 plus 2? That's pretty easy, 4.9. And a limit, again, is a process. We're trying to see where these outputs are going. So we choose a number even closer to 3. Now, 2.8 would be closer to 3, but we want something a lot closer to 3. So like by a factor of 10 or 1/10 or however you want to do that. Like 2.9 is 1/10 away from 3. 2.99 is 1/100th away from 3. And you can see 2.99, I'm trying to do this with really easy numbers so you know where they're going. Plus 2 is 4.99. Can we get closer? Sure. 2.999, 1/1000th away from 3. Plus 2 gives us, oh my gosh. So we kind of know where things are going. If we filled in this table more, well, obviously, the left-hand side, we would do like 2.99999, right? 999 thousandths, 10 thousandths. And we're going to get it. The number isn't all that important. It's the trend of where the numbers are going. And the idea is, 4.9, we can see 4.99, 4.999. What matters is where these are going. And where they're going is getting closer and closer to 5. So the way we say that, we're going to rewrite. We're not going to be lazy and like write equals 5 way back up here before we did our work. The limit as x approaches 3 from the left of x plus 2 is equal to 5. And what we're saying is, as we choose inputs, a little bit less than 3, getting closer and closer to 3, and put those inputs into x plus 2, we're going to get outputs that get closer and closer to 5. So before we do the other one-sided limit, I'm always going to use the same type of inputs, but I want to show you that it doesn't really matter what the inputs are because we're looking almost like a direction where the y's are going. So if we were going to evaluate x plus 2 at 2.8, what do we get? We get 4.8. And, thinking about what we had, 4.8 is not wrong. It's not 4.9, but the idea is 4.8 is kind of close to 5, so we didn't get anything crazy. And then, 2.98 plus 2 is 4.98, and notice that's closer to 5. 2.998 plus 2 is 4.998. So in this case, we still get the same idea as the inputs get closer to 3, so long as they're a little bit less than 3. The outputs of x plus 2 get closer to 5. And the reason I bring that up is we always just use x as an input to most functions because it's easy, or I don't know, maybe that was my algebra teacher back when I was in junior high. So we might as well use numbers like 2.9, 2.99, 2.999, and then maybe if you need more, just keep getting closer and closer to 3 or 5 or whatever the input is. You don't need to be fancy. It doesn't really matter where the exact numbers that you use in an input, so let's not really think about it. So if we're going to do the limit as x approaches 3 from the right, and again, we're thinking about a number line. We're going to choose inputs that are larger than 3 and getting closer to 3. What would be a great first input? Well, from the left, we use 2.9, something that's 1/10 less than 3, so we might as well use 3.1, something that's 1/10 more than 3. And 3.1 plus 2 is 5.1. And you can probably guess that we're going to be getting y values closer and closer to 5. But again, make sure we're doing this limit process, thinking about a sequence of inputs, giving us a sequence of outputs, or at least the outputs trending in a direction. So 3.01 plus 2, 3.001 plus 2, and we can see that the limit as x approaches 3 from the right of x plus 2 is 5. And that's how we read that. The limit as x approaches 3 from the right of x plus 2 is equal to 5. And again, what we're saying is, if you choose inputs closer and closer to 3, the outputs of x plus 2 are going to be getting closer and closer to 5. Oh man, I am not good at this. Okay, so there's going to be some notation over on the right, and it's not as good as the notation we're going to do. So I guess hinting already. So you'll notice, unlike the last one, there's no little floating minus or plus here. So this is what's called a two-sided limit. We read this as the limit as x approaches 3 of x plus 2. But what it means is the limit as x approaches 3 from both sides. We just don't say the both sides part, but we think it. So the limit as x approaches 3 from both sides of x plus 2. We're going to start thinking about the formal definition of when a limit exists. But you should already be able to guess that's 5. And how do we know that? Because we already did the work. The limit as x approaches 3 from the left of x plus 2 and the limit as x approaches 3 from the right of x plus 2 are both equal to each other. They're both equal to 5. And what I'm writing here is, this 5 is the evaluation of the limit as x approaches 3 from the left of x plus 2. Likewise, the 5 below on the right is the limit as x approaches 3 from the right of x plus 2. Okay. So what do I think is not as good? Well, it's something I see in my class, and that is people will just rewrite the limit as x approaches 3 from the left of x plus 2 is 5, and the limit as x approaches 3 from the right of x plus 2 is 5. And that's all well and good, and that's true, but there's actually a difference of meaning between these two statements. The one on the left is saying, hey, what's important? Not only are each of these limits equal to 5, but they're equal to each other. And, mathematicians are a weird bunch. So obviously these are equal because they're both equal to 5, but we want to write that explicitly on the page. So what's missing here is that these two limits aren't equal to each other. So after you wrote that, you would need to go back and say, hey, the limit as x approaches 3 from the left of x plus 2 is equal to the limit as x approaches 3 from the right of x plus 2. And so you might as well just start off with that and evaluate those limits underneath. So if you're asked, hey, does this limit exist? You're being asked to use the formal definition of when a limit exists, and that's this. And so I'm going to relate it back to what we just wrote. the limit as x approaches c from the left of f of x is equal to, well, it says capital L, but that's like L for limit. But what that really means is some number. Okay? So like we did just now, the limit as x approaches 3 from the left, that 3 is kind of like that constant that we're filling in, of the function x plus 2 was a number, and it was 5. Okay? And the limit as x approaches the same number, but from the right-hand side of the same function is that same output, right? Like we got, the limit as x approaches that same 3, but now from the right of the same function x plus 2 is equal to 5. Well, then we can make the conclusion that the limit as x approaches that input from both sides of that same function is that same output, which is what we did. I did not win a prize. That was first period starting. The limit as x approaches 3 of x plus 2 from both sides, we don't say both sides, but I'm just emphasizing that, is equal to that same 5. Okay, so we're going to do a couple of examples, but we'll do that in a companion video.